Let's look at the idea of acceleration in two-dimensional motion. Again, guys, I want to keep repeating this. All of this topic goes back to the same funda that everything can be understood as parts. And we are just doing that with your, basic introduction, with your displacement, right? Your velocity, and now we are looking into acceleration. So the average acceleration is defined as change in velocity divided by time in the xy plane, same funda. And your rectangular components, in terms of rectangular components, it's represented this way. So let me write it off. So it's again left to us to define the way we want. So A is defined as change in your along your x-axis. I think we'll remove this. Yeah. Plus change along the y-axis. So acceleration along the x-axis plus acceleration along the y-axis. This is how we can define the acceleration in two-dimensional motion. So change or acceleration along the x-axis is quite simple. It's nothing but change in the velocity along the y-axis with respect to time, and same funda with. That's it, as simple as that. Okay. Oh, so sorry, by the way, this is average. All this is average. Instantaneous will be after this. Okay, so that's your basic funda. So if you substitute that, we'll get this particular expression. So if you guys want to take one more step, which I have not shown over there. So we have change along the distance, that would be x divided by this square, and change along the y divided by square of this. Again, this is one extra bit. It's not on the screen over here. So we have an example. So velocity is given. We need to figure out the average acceleration. So velocity initial, and this is velocity final. So the average acceleration is change in velocity by change in time. And this in turn is Vf minus Vi divided by time. So Vf is your 3 I cap minus 1 j cap minus of 2 I cap plus 3 j cap. This entire thing divided by 2. And so this would be 5 minus 2 I cap. I'll just write a plus over here, minus 1 plus 3 j cap. This entire thing divided by 2. So this is 3 by 2, 1.5 j cap. Then we have plus 1 I cap. So many units per second square. Okay, so that is your example. Oh, 2. Oh, my bad. I messed something up. Oh, this is minus, guys. My bad. Minus, and so this will be 2. Yeah, minus 2 j cap. Okay, so that is your average. Now we'll move on to instantaneous. How will instantaneous change if I take up the same thing? Say I'm copying the same thing. How will it change? Simple. Yes, all of this will approach limits. Okay, so basically, do I have space? I want to show it here itself so that you understand that it's not a big deal. Limits instantaneous is not a big deal. All that is happening is things are becoming instantaneous. That is, time interval is reducing to 0, and everything else remains the same. Okay, even this remains the same, right? Limit delta t tending to 0 over here, and limit delta t tending to 0, and we have this. So that would give us your ax and ay. Okay, what else are we looking at? I think that's it. So here, instantaneous acceleration as specific movement is derived as the limit of average acceleration as delta t tends to 0. For a curved path, acceleration often point inwards. So this I'll explain. You will not explain now though. You'll understand in time. So in rectangular component it's equal to dx square by dt square I cap plus so on and so forth. I'll not read it out. Okay, let me change the representation over here. So basically this would be equal to ax will be equal to dx dyx by dt, that is the differentiation of velocity with respect to time, or double differentiation of displacement along the x-axis with respect to time, and dy or ay is equal to dvy dt or d square y by dt square, double differentiation, right guys? So that would be your representation, and we have an example. Again, there's nothing fancy happening over here. The directional part is it's might get a bit confusing. If not, everything else is quite simple. So we have been given the particles motion. It has been described in this way. So we'll figure out the acceleration along the x-axis by differentiating it 2 times. So double differentiation of this particular expression. So first thing is, let's look at single differentiation of this particular expression. This will be 6t square. Okay, and therefore your double differentiation will look like, so this will be 12t, right? 12t. Yeah. Similarly, we have ay. And this is 4t square. If you're able to do it in your head, the double differentiation, well and good. You can go with that. But I'm just showing step by step. So when we derive it first time, when we take the differentiation of this expression, we'll get 8t. And double derivative of this is 8. Therefore, we have a, which is equal to 12t I cap plus 8 j cap, and at t is equal to 1, a will be 12 I cap plus 8 j cap. So all this is well and good. The direction is where the confusion is. So I'll directly go over here. I think nothing else to discuss from this. Did I get the same answer? 12 and 8. Yeah. Direction. It varies with the motion. For curved path, it is often inwards towards the curve center. So I'll show this actually. And what else? Okay. Now this is where it might look a bit weird. But if you go step by step, as we discussed at the start, it will be simple. This is to do with direction. Actually, we'll get to see direction of velocity and acceleration. Actually, we will get to see both of them. So let me consider a particle moving some way like this. And we'll consider 2 points. Say point 1 is over here, point 2 is somewhere over here. Right? And we'll have our position vector from here to here. Position vector is represented by R in general. So we can call this as point A and B. Now, so we have to discuss this actually. Say this is moving with a constant speed. Okay, we'll assume that it's constant speed. So the length of the vector will not change. So I'll make one assumption, constant speed. It makes my job easy actually. Say the tangent is something like this. So that is your velocity at point A. And the tangent is something like this at point B. Okay, so it looks something like that. Not exactly, but again, it's not an exact thing. If I have not drawn something right, don't mind that, huh? So this is your change in velocity. This is how the particle is moving. So this you guys understand. If the particle was moving the other way around, then this would have been my initial point. This is your final point. My tangent would have been pointing towards the left. This also will be pointing towards the left, right? All of that small things, I hope you guys have understood by now. Next, your acceleration, we can figure it out by doing this. Copy this, paste it. Then copy this, paste it. Okay, so we have this, right? This is the key thing. We have to move from, okay, yeah. Guys, how do you represent change over here? The particle, forget about this being Vi and Vf. Think about this as a position vector. Let's imagine this is a position vector. The particle moved from here to here. So what is the change? How does the change look like? A line joining this. Do you guys agree? Because this is velocity, this we can term it as change in velocity. That's the direction of change in velocity. The direction in which the velocity changes is the direction of, that's your direction of acceleration. That's it, as simple as that. So what are the steps? First, you have to have the graph or the path of the particle per se, right? That we got to see. So the particle is moving in this xy plane in this manner. Then I considered 2 points and we found the initial velocity and the final velocity. And all I did was use vectors to arrange them tail to tail. Remember, this is tail. And we know if a particle is moving from point A to point B in this manner, the change in velocity will look like, joining from initial to final this way. The direction in which your change in velocity point towards is the direction of the acceleration. Okay, as simple as that. Right, let me remove the graph also. So this is it. That's your direction of acceleration. Okay, and if you see one point that kept repeating, the curved path, whenever we see a curved path, the acceleration often points inward towards the center. So if you look at this space And if you can imagine that this is a circular path, can you see that it's pointing inwards? This direction is pointing inwards. If I take the mean, if I happen to position all of this over here, you can see that it's pointing inwards. Okay, so that's one thing that you guys have to make a note of. That's one trick, right? So we have the direction of acceleration pointing inwards. Anything else? In one dimensional motion, an object's velocity and acceleration are always aligned along the same straight line, either in the same direction or opposite direction. This we saw exclusively, right? We kept seeing this in our motion conversation, one dimensional motion. While in two dimensional or three dimensional motion, the angle between the velocity and the acceleration vector can range from 0 degree to 180 degree. So this we saw clearly. Here the angles are nowhere, 0 or 180 degree. It can vary anyhow it wants. It goes situation by situation. So that is one small note. Okay, so yeah. So we just got introduced to the entire chapter. Literally. We started off the chapter by looking at the key idea, that is to break things up and then start looking at it each axis part by part and combine them, end of it. So this also was applied to your displacement. The same thing was applied to your velocity. And now we are applying it to your acceleration. So acceleration, the definition will not change. Nothing changes over here. It's just an advanced version of, or a extra bit of work in each axis basically. Okay. And then we saw average acceleration, which is quite simple. Instantaneous acceleration also has a definition, it's quite simple. Direction is where the complexity comes into picture. Direction of velocity, direction of acceleration, it looks a bit complex. But if you go step by step, it's very simple. If you use common sense, it's very simple. The direction of acceleration will make a lot more sense when we learn about force. So till then, if you guys are a bit patient, it might look a bit weird. Why is it pointing this way? But you'll understand when it comes to force and everything. Okay, so it's time for you guys to start copying. For this write-up, this is my write-up. And then we'll move on to this. This is my write-up. Then we have an example also. Yeah, it's over here. Now you have to talk about the directional aspect. And then you have to copy this must. Oh, sorry. Yeah,